In the previous video, we saw that the limit comparison test is easier to use than the direct comparison test. However, it still has the limitation of needing another series to compare the original series to. There are some tests which allow us to use the terms of the original series themselves to determine whether it would converge or diverge. One of these is known as the ratio test. It is based on the idea that in order for a series to converge, the terms of the series must shrink to zero fast enough to overcome the fact that we are adding an infinite number of things together. So as long as the things we're adding are shrinking in size, are getting smaller and smaller and smaller, as long as they are getting small enough, fast enough, then the addition of an infinite number of things will result in a finite sum. We can show this then by looking at a sequence of positive terms and evaluating the limit as n goes to infinity of any term in ratio to the term immediately preceding it. Now, the idea is that we already know that the terms would be getting smaller. If they weren't, then we already would know that it diverges by the divergence test. So we know that the terms are getting smaller. So what happens here is that we have the term in the top will always be smaller than the term in the bottom. If then this limit comes out to be small enough, specifically if the limit is less than 1, then it means that the terms are shrinking fast enough that the ones in the top are, the term in the top is always shrinking by a little bit more than the previous thing. That is to say, if we were to compare A2 to A1, we would know that A2 is smaller. So it is a certain ratio smaller than A sub 1. If that ratio were to stay consistent, then the terms would be decreasing at a very, very constant rate. If that ratio is smaller than 1, that means that each subsequent ratio is smaller than the ratio before it. And that means that the terms are decreasing in such a way that the subsequent term is decreasing faster as we go further and further out the series. In that case, the series would be able to converge. If L is greater than 1, including infinity, then the series would have to diverge. The only way for the ratio to be bigger than 1, or the limit to be bigger than 1, is if each new ratio is actually bigger than the previous one, which means that the amount that the terms are shrinking by is not as much as the one before it. They're just not shrinking fast enough anymore. If, however, L is exactly equal to 1, then it means there is a consistency to the shrinking of the terms that leaves us with the situation that the test is inconclusive. So it is not a foolproof test. It is simply another alternative. So this is going to consist of taking the n+1th term of a series in ratio to the nth term of a series and seeing how that limit evaluates. Like we saw in the limit comparison test, if we are taking the limit of a ratio, there is a good chance that we may need to employ L'Hopital's rule. So we may see that come up. However, that is not always the case. Let us look at some examples. Consider the series 3 to the n over n cubed. The idea here is to look at the terms and see if, in ratio to each other, they shrink fast enough. Now actually, if we play with the listing out some of the terms, we will see something that happens here. When n is 1, we have 3 to the first over 1 cubed. Then we have 3 to the second over 2 cubed. Then we have 3 to the third over 3 cubed. Then we have 3 to the fourth over 4 cubed. And then 3 to the fifth over 5 cubed. And while we do see in the first three terms that the terms do start to shrink, when we hit the fourth term, we can see that now the terms are once again bigger than 1. By the time we hit the fifth term, we are almost up to 2. The numerator is almost twice as big as the denominator. So it's pretty clear here that by the divergence test, this series will diverge. Now you might say, if we already know this, why would we do the ratio test? Well, it helps to see, doing the ratio test, how the result matches what we said it should do. So by the ratio test, we would be looking at the limit as n approaches infinity of 3 to the n plus 1 over n plus 1 cubed over 3 to the n over n cubed. So the formula for a sub n with n plus 1 substituted in over the formula for a sub n itself. Like with the limit comparison test, this is a complex fraction and will result in a multiplication by the reciprocal of the denominator. Now there is some cross-simplification that can go on here. The more obvious situation is the 3 to the n plus 1 in the numerator with the 3 to the n in the denominator. 3 to the n plus 1 is literally one more factor of 3 than what we would have in the denominator. So they would simplify to having a single factor of 3 left in the numerator. This would give us 3n cubed in the top over n plus 1 cubed in the denominator. Now it's not terribly difficult to expand the n plus 1 cubed, but it is a polynomial, and the numerator is also monomial, but a single term polynomial. So in expanding the denominator, all we really need is the lead term of it. And again, if we wish to go through all of the steps of L'Hopital's rule, or the calculus 1 technique of multiplying the numerator and denominator by 1 over n cubed, in either case, we would see that eventually this comes down to be the ratio of the lead coefficients, because they have the same degree. This is bigger than 1. By the rules of the ratio test, this series diverges, which matches the conclusion we had at the beginning based on the fact that the terms do not drop to 0. And that's what we see here, is that the terms, the further out in the series we go, the terms are actually going to approach a value of 3. Now, that's not the easiest to see at the beginning. We can see the first term is actually equal to 3. The second term drops to just slightly bigger than 1. Sorry, the second term drops to slightly bigger than 1. The third term drops to 1 itself. But then the terms start to get bigger again. If we were to continue listing out terms, we would see that eventually, and writing their decimal equivalents perhaps, we would see that the terms eventually are approaching a value of 3. And again, the only way that a series can converge is if the terms are approaching a 0. So what we're seeing here is that the terms are getting bigger. Each new one is roughly going to be 3 times bigger. The numerator is going to eventually be 3 times bigger than the denominator. The ratio of the terms is going to be approximately 3. So each new term is going to be approaching 3 times bigger than the one before it. So they certainly cannot be shrinking fast enough. For another example, let us consider the series 2 to the n over n factorial. Factorials, recall, are a discrete operation, and because of that, the integral test cannot be applied to them. The direct comparison test perhaps could, but since factorials are a bit unusual to us, perhaps finding a comparison series to them is not as easy as we might think. The same thing with the limit comparison test. However, the ratio test is very, very well suited to dealing with factorials, as we will see in a moment. The n plus 1th term would be 2 to the n plus 1 over n plus 1 factorial over the nth term, 2 to the n over n factorial, which, as we've seen many times now, would become the product of the numerator multiplied by the reciprocal of the denominator. As we saw in the previous example, we get a cross simplification of the exponential terms, which makes exponential terms very good with the ratio test. The ratio test works very well on them because there is a convenient cross simplification. Now, a bit less obvious is the factorials, because again, we're less familiar with them. But n factorial is 1 times 2 times 3, and so on, up to n. And n plus 1 factorial would be 1 times 2 times 3, it's so on, up to n, and then times n plus 1 as well. So what we would have here is a cross simplification of every single factor in the product, except for that last extra n minus 1 in the denominator. The same way that exponential functions work very well in the ratio test, factorials also work very well in the ratio test. Almost everything cross-simplifies until we're left with a single 2 in the top and a single factor of n plus 1 in the denominator. And this limit clearly is equal to 0. This is certainly small enough for the terms to converge, or for the series to converge. If we want to list out the terms, we will see that they definitely shrink to 0. 2 to the first is 2, and 1 factorial is 1. 2 squared is 4, and 2 factorial is 2. 2 cubed is 8, and 3 factorial is 6. We now get to see the terms starting to shrink. The first term is equal to 2. The second term is also equal to 2. The third term is smaller than 2. 2 to the fourth is 16, and 4 factorial is 24. This is now smaller than 1. 2 to the fifth is 32, and 5 factorial is 120. The numerator will continue to double each time, but the denominator will not double each time. It will increase by a factor equal to n. So the next denominator would be 120 times 6. And then the next one would be that value times 7. So the denominator is going to grow incredibly quickly compared to the numerator. These terms are going to drop to 0 in a big hurry. And therefore, the ratio of the terms also is going to drop to 0. Because the terms are shrinking so fast, the next term is going to be so much smaller than the previous one that the ratio of them will continue to shrink as you go. And that's what leads that limit to be 0. Thus, since this value is smaller than 1, the series 2 to the n over n factorial converges. The terms shrink to 0 fast enough to overcome the addition of an infinite number of things.